So good afternoon in Taiwan and good afternoon in Australia. And today it's really a special occasion that we have Dr. Matheus Manzatto de Castro from the University of New South Wales. And he's going to tell us about his recent research and thought about what happens if we introduce noise to the deterministic system. Yes, and we are very curious about his insights, so let's welcome him.
Okay. So thank you very much. So I'm Matheus, that was being said. So I will be talking about stochastic stability of equilibrium states via quasi-ergodic measures. So this is a joint work with Bernat Bassos-Fernandelias, who is also not anymore, right? He's a PhD student at Imperial College, and Jeroen Lambe, it was my supervisor during my PhD. So my talk, there will be a lot of parts, so there will be a really big motivation. So these two parts are basic motivations. Then I will be briefly talking about the stochastic stability and conditioned ergodic theory. Then I will be combining these two areas to talk about my results. So the results will be talked at the end. So as motivation, so this is a talk about dynamical systems. So we will be talking about the quadratic family as motivation, right? So I'm choosing a element of the quadratic family, which with a very special parameter here. So this map of the quadratic families is in the three periodic window, if you're familiar with that. If you're not, it will be in just a bit. So one can show that one of the properties of this map is that it is called axiom A. So if you go to the book of the Mellon Van String, one-dimensional dynamics, they call it will satisfy what they call their axiom A. So there will exist for this map a finite attractor A, which is in this case is a three periodic orbit. That's why I said that is in the three periodic window. And if you define BTA as the basing of attraction of this map, then the complement of it is a hyperbolic set. What I mean by this is that there exists some CNR such that each point that you take for this set lambda, its derivatives will increase exponentially fast. So what is worth to mention here is that this basing of attraction, it will have full Lebesgue measure. However, there will be a set here which is responsible for all the chaotic behavior. There will be a counter set here, which the dynamics under this lambda will be chaotic. So if you look to try to do to see how is the dynamics of this map. So what I'm doing here, I'm uniformly sampling some points from -1 to 1. I'm taking, I think, 1,000 points. And what I'm doing, I'm just iterating these points and printing the result here. So you can see that after not many iterations, more or less 250, let's say, so all these points, they are going to this three periodic attractor. However, what is interesting to consider is to take one point here and see what is happening when you iterate. So what is the path of one of the points here? So what you observe when you do such procedure is that the map will have some sort of really chaotic behavior here, which reminds a bit of Brownian motion. And then out of nowhere, it will go to order. So this is something that it happens in a lot of physical systems, and physicists, they have a name for this type of behavior, which they call transient chaos. So it's when your system goes to a stage which is completely chaotic and unpredictable to something that is extremely ordered. Okay, so what I'm doing here, just for the records, is that I'm taking one point and I'm just printing each third iteration of this point. I'm just doing this because since it's going to a three periodic attractor, I want to go to something that reminds a fixed point. And of course, this is not only For one-dimensional systems, this can be observed as well in two-dimensional systems. So for instance, if you look here to a Hanel map, so there are a lot of definitions of a Hanel map on how to define a Hanel map. So this is one of them. But if you take this map and very specific parameters A and B, here that is A is 1.25 and B 0.3, you are in a regime that you have a 7 periodic attractor and the repeller of the system is hyperbolic. So if you try to do the same type of plot, so what I'm doing here is just trying to plot the first coordinate of the system and see what happens to a point, you see again that you have something that is extremely chaotic and reminds a Brownian motion until at some point out of nowhere you go to something that is extremely ordered. So you have some sort of synchronization. It's also worth to mention that this is extremely sensitive to initial conditions, the amount of time that happens before ordering. So for instance, here in the simulation here, we're starting at these points, okay, this X naught and Y naught. And in the second one, we are just shifting X by this amount that is extremely small, right? But the time that you take to go to this stability is reduced by like to 3.5. There is more or less 3.5 less time to go to synchronization. Okay, and this also happens in some physical, actually a lot of physical systems. For instance, one that one can be observed this type of behavior is in this Duffy oscillator. So it's an extremely complex circuit. But what is important to notice here, so I will be making a zoom on this part here, is that this circuit has one thing which is called feedback. That is, the output of your circuit is going back to the input of the system. So this generates some instability and your system needs some time to stabilize. So what you see here, so I'm taking this point and these 2 points and trying to compute the difference of potential of these 2 points over time. So this is in milliseconds, okay? So what you see is that you see something that is extremely similar to what was happening before. So it's extremely chaotic until at some point that is close to 3 seconds, you have a complete order. So you find this type of behavior. And what physicists want to understand, for instance, is how long you should be taking to obtain this stability of your system. Okay, so they have some explanations to why this should be happening. One way that they try to explain this is via what they call natural measures. So let us go again to our toy model, okay, and try to see what the procedure that physicists do to try to explain this behavior. So what they conjecture in some sense, and which is in this case of this toy example is true, is that the chaotic behavior is what is responsible for the chaotic behavior is that you have some repeller in your system, and using some sort of ergodic theory or something like this, it should have some invariant measure in the repeller, which is more important than others. And they would like to detect what is this measure in some sense. So what they do is to define this notion of natural measure, which doesn't really have a formal definition. What they have is a procedure to obtain this natural measure, which goes more or less in the following way. So bear in mind that this is not the unique way. There are a lot of algorithms to compute this measure, but they are all more or less like this, okay? That's how I will be describing. So you will be taking your state space, which is in this case is -1, 1, and you will be choosing some n0 which is big that you will be partitioning your state space. So you have -1, 1, and you are just partitioning it in any zero components, which I have written here. After this, you will be choosing some n1, which is much greater than n0, such that in each element of your partition, you will be uniformly sampling a sequence of points in each element of the partition. So you had your 0, 1, you had your partitions, and then you will be choosing a lot of points in these elements of the partition. So the next procedure is to, again, so remember that we are trying to understand the behavior of points in the repeller. So you need to detect the points that more or less stay close to the repeller. So the next stage, it will be to find some, to find the attractor and try to understand what would be a neighborhood of the attractor. Then you would do some exclusion. So the next part is to try to find the attractor here, neighborhood of the attractor. So to do this, what they do is like you will be choosing some n2, and you will be defining this lambda Tn as the finite time Lyapunov exponent. And you will be defining the neighborhood of the attractor, Bn2. So recall that this n2 is independent of n1 and n0, are just points in -1, 1, such that it's negative for each iteration. So it's really a neighborhood of that attractor. So remember that if it is in that attractor, so the Lyapunov exponent here, it will be negative, all the Lyapunov exponents will be negative. So you're just taking the points that are close to this three-periodic orbit. And then finally, you will be defining this delta n being the points that never reach this neighborhood of the attractor. So you want to find just the points that are close to the repeller, always close to the repeller. Not always, but up to time n. And what they do, there is yet another choice. So an n3 now that is much greater than 1. And what they define is that this measure, mu, the natural measure in this element of the partition, PS, it would be the following. So you would take the points that did not reach the attractor, that did not leave the repeller, so it never reached this neighborhood of the attractor. So in each of these points, you will be just taking a Birkhoff average of it, and then you will be taking an average of the points. So that survived. So what we're doing is basically a condition histogram. So you were taking the points that lie in this element of the partition, PS, and then you will be averaging it by the points which survived. So this is a really complicated procedure. There are a lot of choices that depend one of another. It seems that there is absolutely no hope to converge these things. However, if you put this in a computer, what you obtain, and you always obtain actually, a picture that reminds a lot something like this. So initially you may imagine that this has some numerical error because it's extremely spiky. However, I guarantee you that if you put in your computer for some magical reason, you will be obtaining a picture which is really similar to this one. So something really weird is happening, right? So what I will be trying to do now is to propose a slightly different method of obtaining the measure, okay? And the method will be based on Markov chains because they are slightly nicer, right? They are well behaved. So recall that we have our attractor, our three-periodic attractor, and we are looking to this quadratic map here, right? So what we'll be choosing is U being a neighborhood of this attractor. So we choose an open set U, which contains the attractor and is contained in the neighborhood of the repeller, okay? And now I will be inducing a Markov chain, which try to mimic the procedure that they had proposed. So my Markov chain will be the following. Okay, we will take some epsilon, which is small. Okay, and we will, and my Markov chain is the following. Okay, it's a Markov chain on R. That is, if I'm in -1, 1 minus the neighborhood of the attractor, then I will be iterating my map and adding a small noise. Okay. If I'm not, if I escape the interval -1, 1, or if I'm in the neighborhood of the attractor, then I stay still. Okay, so this is my Markov chain. So a picture is something like this. So I have my M, that is the region of interest, and I have the complement of M, which I'm calling here partial due to historical reasons. Okay, so I will be iterating my map, my Markov chain. So if I go out my region of interest, then I stay still. Okay, observe that this is what people in Markov chains call an observing Markov chain, because if you are impartial, then you stay still, right? If X analyze impartial, then next iteration is impartial because I'm staying still. So I have what they call an observing Markov chain. Now the idea is try to do the average that they were doing in their algorithm to obtain the natural measure. So we will be defining this stopping time, tau being the minimum time which you escape from M. So you have your -1, 1, you have your neighborhood of the attractor, something like this, and you start iterating your dynamics. If you want to understand the points which the minimum time to either hit this neighborhood or to leave -1, 1. Okay, so what we'll be trying to do now is try to do exactly the same procedure that they have done. So we would like to understand so I will be taking a set A, a subset of M, and I will be looking to the Birkhoff averages conditioned upon staying on M, on not escaping. What I mean by this condition is like a condition probability. So I'm just taking the expectation of these points, and I'm just looking to the noise realizations that stay up to time n, and then I'm normalizing it by the probability of the points not escaping. So I did not really write here, but this px here, okay, it means just the probability of something happening given that your chain start at x, okay? So I would like this, if n goes to infinity, this to converge to something. So look, for us, the theory of observing Markov chains studies exactly this type of conditioned Birkhoff averages. And there is a measure which this converges, which is called a quasi-ergodic measure. So the definition of a quasi-ergodic measure, it's a measure where for nu, almost every x in M, when I look to the conditioned Birkhoff averages, I converge to this, I have this non-trivial distribution. And now what I would like to do is to take this epsilon to 0 and see if I have something that looks like a distribution. And it turns out that if you just put this in a computer, and it's really easy to compute these measures, knowing that they exist, of course, and I will be telling you how one should be computing it in the future. So if epsilon goes to 0, you obtain a picture which is really similar to the natural measures of the physicist. So the talk is more or less about to understand these pictures. So why do we have something that is similar to one another? Okay. So to do this, we'll be talking about stochastic stability and condition ergodic theory, because this type of limit, it appeared before or in the literature, not exactly in this context, but in a different context, that is in the context of stochastic stability, to try to understand this behavior of limiting measures. So I will be talking about this just to say some motivation. So this problem of stochastic stability, it backs to Kolmogorov, and the idea is more or less the following. So suppose that you start with some map T that goes E to E, a dynamical system. So in a lot of cases, you have several invariant measures, especially in the case that you are that your T is hyperbolic, for instance. You have a lot of invariant measures, and then the question of Kolmogorov is which is the most interesting one, right? And the method that Kolmogorov proposed is more or less the following. So suppose that you take some Markov chain, xn, epsilon, which is close in some sense to your original dynamics T. And I will be more precise what close means in the future, but let's just imagine that I have a Markov chain which is close. Then when we are looking to these perturbations of this map and trying to construct a Markov chain to it, which generally you obtain, especially if your perturbation is something that spreads the dynamics, some sort of diffusive noise, and so on. So it's in a lot of cases you have a unique invariant measure for a unique stationary measure for the Markov chain. So unique stationary measure. So in this context of which is the most important invariant measure, in the context of Markov chains, is not a huge deal, because in several scenarios you have a unique stationary measure. So the question of Kolmogorov is that if epsilon goes to 0, to which invariant measure do you converge? If you converge to some measure, then you have stochastic stability. So what I will be showing now is a simplified version of stochastic stability, okay, that is as the following. So I will be erasing this this was just motivation, right? So now, if you consider again this map that I was saying, T that goes E to E, so let us assume that you have a unique physical measure. So what I mean by this is that I have a unique measure mu, such that when I look to the basing of attraction of this measure, I have the basing of attraction of a measure are the points in E, such that the averages converge to its integral for all continuous functions. Here it was supposed to be an E, okay? And assume that I have a unique one that is a physical measure. That means that when I look to this basing of attraction, the Lebesgue measure of the basing of attraction has a Lebesgue measure greater than 0, okay? So one way of trying to study stochastic stability is, suppose that now I take some epsilon greater than 0, and I take a family of Markov chains, such that when I look to the perturbation, I look to the transition kernel of these Markov chains, when epsilon goes to 0, you are converging weakly to the Dirac measure of T of X. So that's what I meant by Xn epsilon being close to the map T. Now, as I was saying before, the question of stochastic stability is in some sense under which conditions on the perturbation and on T, that when epsilon goes to 0, I will be retrieving an interesting measure, which in this case should be my physical measure, okay? So there is a huge literature on this topic. So there is by the way, so this is, I do not meant to by any means for the list of reference that I'll be showing to be comprehensive. Okay, this is just some papers which I know. Okay, so in the uniformly hyperbolic systems, for uniformly hyperbolic systems, these have been massive. There has been a lot of works on this area, and probably is the case that we're most of these are works of Kiefer, Lysen-Young, and Baladi. Also, it's known, it's a bit less known, but people have some results on the non-uniformly hyperbolic case. For instance, for unimodal maps with Collet-Ekman condition, there are really nice work of Baladi and Viana. Also for non-uniformly expanding endomorphism, there is a work of Alves and Vilarinho, and non-uniformly hyperbolic diffeomorphisms, also Alves, Araújo, Vasquez, and also a really nice paper of Young and Connerson. However, what is interesting to observe is that this notion of stochastic stability, like you cannot do it, at least not in a trivial way, for maps with hosts. So for maps with hosts, what I'm defining here, so it would be some T that goes E to E, and this E again, due to historical reasons, I'm writing it as M union partial. So you would like to find this map, this lambda, an invariant set of the points that never leave M. So, and then what people in dynamical system with host tries to understand is like, what can we say about the dynamics from going from lambda to lambda? Which, if you think a bit about it, it is similar to the type of situation that we were dealing in the natural measure. So you would have some repeller here and some attractor, and you are in a situation that points are leaving the repeller, points close to the repeller are leaving its neighborhood to go to the attractor, and you would like to understand the information about the repeller, knowing just the whole map, right? However, you cannot really do stochastic stability in this context because, well, the points will never accumulate in the repeller, right? So any type of physical measure that you try to obtain, it will be supported on the attractor. So the try to do stochastic stability is slightly unclear how to do in this case. However, there is a theory that which may be used to just be able to do this stochastic stability, which is the theory of conditioned ergodic theory that I will be briefly describing. So let us start with once again a motivation. So if I have this really simple Markov chain, so it's A, B, C, and D, and it is behaving according to these graphs, okay? Sorry, these zeros. Then if you want to understand what are the statistical properties of Xn on this state space M, it's extremely simple, right? So you can obtain all the statistical properties via the transition kernel. So if you define, the transition matrix. So if you consider this probability matrix such P, such that its entries are Pij, and I just defined that is the probability of line in J given that you started in I, then what you can do is just using Perron-Frobenius theorem to obtain a right eigenfunction of this transition matrix. And the whole thing is that Birkhoff-Ergodic theorem tells you that, because you know that this chain is mixing, right? You obtain that now you have a lot of properties, right? But probably the weakest of them is the law of large numbers, that when you will be looking to the, well, I take just A, I look to the Birkhoff average, this will be converging to the measure of this vector seen, this probability vector seen as a measure, right? So I will be now slightly changing my Markov chain here. So what I will be doing is just killing, just to removing this this edge here. So what you can do, and you can easily observe that all the points here are going to D. So it's not interesting anymore. However, if you are in a situation where this probability here from going B to D is really small, something like this, you would see, and you try to put this in a computer, you would see that you would be going first to a non-trivial distribution here before you are leaking out. So the theory of conditional ergodic theory tries to understand what is this limiting distribution that you would be seeing here. So if you try to be slightly more precise, now what you really would like to do is try to understand. So if I define tau as the minimum such that I escape my M that is now ABC, right? So the minimum time that I reach D. So what you would be really looking for is trying to understand something like this. So the Birkhoff average given that you did not escape. However, this makes absolutely no sense. So the way to try to make sense out of this is just putting an expectation here, okay? And now you would like to understand where I'm converging to. This problem was solved by Darroch and Sanata, and what they showed, Sanetta actually, and what they have shown is that now if you consider the same transition probability, sorry, the same transition kernels as before, okay? So now it will be a matrix that I and J goes, let's say it's a 3 by 3 matrix, and I obtain a substochastic matrix exactly in the same way. I can still apply Perron-Frobenius theorem to substochastic matrices. And what you obtain is that in this context, that the spectral radius is now something that's in between 0 and 1. You have left and right eigenfunctions. And when you look to the Hadamard product of these two probability vectors, so what I mean by this is just I'm taking each entry, multiplying, and then I'm normalizing to obtain a probability vector, right? So what they have shown is that this condition Birkhoff average goes to this to this non-trivial distribution. So you have a characterization of these conditioned averages. Well, now you can do this to a general setup, okay, to try to aim to do some stochastic. So we have a theory which tells us how the condition average should be behaving, and we may be able to do this in general, right? So in a general setup, you would just start with a Markov chain on E, and E would be decomposed as M union partial. And we want to start absorbing Markov chains, so we are assuming that it's absorbed at partial, as I said before. So if you were in partial, you remain partial forever. And given a measurable set A, we'll be just defining PXA as the transition kernel of this chain, right? So is the probability of X1 line A given that you're starting A. And again, since we want to do condition average, we once again define tau as this stopping time. Okay, so now what we need to do, as in theory, right, is try to obtain some objects that will help us to understand the statistical behavior. So there are two main measures of interest that you can try to use. So one of them is the quasi-stationary measure, and the quasi-stationary measure, its role is to mimic what the stationary measure is for the not deterministic, but in the case without escape. So if I take a Markov process Xn, so mu will be a quasi-stationary measure if I have this relation. And since I'm in a case where I have escaped, so this lambda now is in between 0 and 1. So remember that if you want to find a stationary measure, then this lambda would be equal to 1, and you would have something like this. But since we have escape, we need to put a constant here. And the second measure of interest would be conditioned, one that behaves well under conditioned Birkhoff average. So we define mu as a quasi-ergodic measure if for any age that is bounded and measurable, when I look to the conditioned Birkhoff averages, I go to some distribution. So it's worth to mention that these two measures, different from the case without escape, these two measures, they tend to be different. Actually, they are always different unless you are in a situation where things are quite pathological. Okay, so to find these measures is extremely easy. Let me rephrase. So to find quasi-stationary measures, it is not too complicated because you can try to solve, because it only consists of finding an eigenvalue of an operator. So you have some linear operator, you need to find some eigenvector, and there are a bunch of theory that helps you to do this. Like, for instance, my favorite one is Banach-Lattice theory. Okay. However, the problematic part is to find the quasi-ergodic measures. So the existence of quasi-ergodic measures is extremely unclear, and it comes from the fact that there is no natural eigenfunctional equation that will allow you to obtain its existence. And this comes from the fact that, once again, if you just try to expand what is this condition Birkhoff average, so it is something like this. So observe that both parts, these and these, are going to 0 exponentially fast. So the existence of this limit requires some non-trivial cancellation here. However, there is some hope because there is a conjecture, a folklore conjecture, and I'm calling it folklore conjecture because it's not stated by anyone. However, if you look in the literature, a lot of papers goes to try to always show this type of result. And the conjecture would go something like this. So if you obtain an observing mark, and the conjecture is basically what happens in the discrete state space would be happening in general. So if you have some xn, which is an observing Markov chain here, and observed at partial, so the conjecture says that if you have a quasi-stationary measure, okay, with, I did not say, but this lambda here, we call it a survival rate, okay, with survival rate lambda, and you have a right eigenfunction, and you have something which is called conditional ergodic, which was slightly hidden in the example that I was showing. That is something like this. So if you're in a situation that here is M and here is partial, and I have a set A such that for mu almost every point in A, I either stay in A or I escape, then the set A should have 0 or 1 measure, okay? So this is what would be ergodicity in this context of scape, right? And the conjecture goes that if I have these three things, then if I combined left and right eigenvectors, then I should be able to obtain my quasi-ergodic measure. And observe that if this conjecture is true, then it's easy to compute using a computer what the quasi-ergodic measure should be, because you can easily discretize this operator. You can do some Ulam method and compute left and right eigenvalues and combine them to obtain this measure. This conjecture has been verified in a lot of contexts. I will not be going through all of them, but like in discrete state space has been shown. like not entirely, but almost birth and death process, stochastic differential equations, and I have been working a lot in during my PhD to try to establish the existence of these measures in discrete time Markov processes in general metric spaces, which is the setup that we are interested here, right? So now I talked about the stochastic stability and I talked about conditioned ergodic theory, and we have now a natural measure that we could try to use to define some notion of stochastic stability to maps with holes, right? So going back to our toy example, so it's just the logistic map with a bit of noise, right? So the first thing that we have shown is the conjecture holds for this map, the folklore conjecture. So if you look to this operator, you can show that the spectral radius is greater than 0. And then when you combine right and left eigenvalues, you obtain a quasi-ergodic measure. So you are really good so you're in a good situation to try to start looking to the problem when epsilon goes to 0. What is really interesting now that what we managed to show is that if epsilon goes to 0, this indeed converges to a measure when epsilon goes to 0, it converges in the weak star topology to a measure, and the log of the value of the spectral radius also goes to a different value. So here is weak star, but it should not be weak star. These two are real numbers, and we can characterize these values. Okay, so mu0, it will be the unique equilibrium state associated to the map T, associated to this potential on the repeller. So if you look to the thermodynamic formalism theory, we can completely characterize this measure. And here I briefly recall what is an equilibrium state. So if you take a dynamical system, T that goes x to x, T invariant measure nu is an equilibrium state for this potential psi. If when I look to the metric entropy plus this integral over the potential, then it is a measure which the name of this, which realizes the supremum. Okay, so this is the definition of equilibrium state. So this has some relation with the statistical mechanics, and it has a lot of development on the theory of dynamical systems. And this P0 that you are converging to, it's the so-called pressure that is exactly this value. Okay, so this is a real number, and P goes to P0 is exactly the supremum with this potential here that is minus log of dt. It's worth to mention that this is, for expanding maps, this is a really important potential because it gives rise to, if you people are familiar, to the SRB measure for endomorphisms, right? Expanding the case. So, and then the picture is more or less very, now it makes sense, right? So the picture is justified because this is going to this equilibrium state, nu0, and due to spectral gap, in some sense, one can show that also this natural measure, it will go to the same measure. So we understand well why these two objects, they are similar, right? So one thing that always annoyed me, let's say, in the theory of stochastic stability is that you cannot talk about the other equilibrium states, right? And this method also allows you to approximate the other equilibrium states of the map. So I told you what was to condition upon a set. Now I tell you what is conditioned upon a function, and it's a really natural definition. So if you take H, which is in L infinity, and F, which is in L1, and positive, so age condition upon a function, it's just to take the product of these two functions, and then I normalize by the average of f. Okay, and now what we can try to do is to consider Birkhoff averages condition upon this function, where this Sn phi is the Birkhoff sums of a potential phi with my Markov chain. So although it may seem slightly non-conventional, this type of condition, I tell you that this has been massively studied in the literature. So this is part of Feynman-Kac formulae, if you are familiar, and it's something that has interest in physics. So there are a whole branch of probability which they look into this type of limits for stochastic processes. And if another thing is that if this measure converges to something, it's called a phi-penalized quasi-ergodic limit. Okay, and what we have shown as well is that for this system here, when you look to this new operator, which is the same one that is used in large deviations in probability, then you would obtain exactly the same thing. So basically the folklore conjecture, it holds in this context here. So you have a positive, you have a positive spectral radius, and when I combine left and right eigenfunctions, then the condition Birkhoff averages here will go to my distribution. And moreover, when epsilon goes to 0, what you obtain is that you will be converging to some measure in weak star topology and to a value, and we can really characterize it using thermodynamic formalism. So mu zero will be the unique equilibrium measure associated to this potential phi minus log of t prime. So recall that when there was no potential, so it was 0, the result was exactly this. So it means that when I put a different potential, I need to pay a price, and this price is minus log of dt. And once again, when I look to the log of the spectral radius, I go to the pressure. Okay, so I managed to do stochastic stability using for a map with hope to understand which is the most relevant in some sense measured in a repeller, even if I have some sort of potential. And now the question is, well, how general is the theorem, right? So I have been doing only for the logistic map, but of course we can just try to do a bit better, right? So it was just our toy example. So you should be in a situation that you have T and you have some sort of hyperbolic repeller here, okay? And you will be choosing some partial, some region that you don't like, right? And you would like to understand what is the dynamics given that you stay in this region M, right? And then you may choose, then it depends on your problem, right? You may be just putting a neighborhood of the attractor, or you would like just to understand the neighborhood of the repeller, okay? So in order to make it work, we need some sort of hyperbolicity, okay? So I'm saying now just how to generalize the previous result. So I will be starting with some map T that goes E to E. It's M compact manifold, maybe with a boundary, such that it is C2. And we say that this map with hole, so the hole here will be some partial, okay? So it satisfies a hypothesis A phi if one, the points that remain M is hyperbolic expanding. So I mentioned here that I'm just saying for uniformly expanding. However, for uniformly hyperbolic, so in the case of diffeomorphisms, it will also work a similar theorem. So we did not put it on arXiv. We did not write this paper yet, but is in the process of being written. The proof is slightly different, than we decide to split into two papers. So, and the second assumption is that T admits a unique equilibrium state for this potential. Okay, so it's important to mention that lambda, it may be separated in several regions. Okay, and you also may have some cyclicity in this counter set lambda. However, I just ask that I have a unique equilibrium state, okay? And also, I'm in a situation that if if the dimension is greater than 1, I need some technical condition that is basically saying that my counter set is not touching the partial here, okay? The region that I don't like, okay? So there is some non-degenerate condition here that is always easy to verify. Okay, so this is what the last part is. Okay, so we need some map which the repeller of it is uniformly hyperbolic. Okay, so this is basically what we need. And the perturbation that we are interested that was defined. So you would make a map T and you take some F epsilon that goes from minus epsilon epsilon. So it is a cube here times E to E. And you would like that these perturbation maps, they are C2 close to your map T. So you take C2 perturbations and then what you do is that you define the same map as before, so the same chain as before. Okay, so if you stay in M, then I iterate. I make a small perturbation. So recall here that T omega x will be just this F epsilon. That is my perturbation. And I take an omega 0 here, this omega 0 being in the cube. Okay, and if I leave the region of interest, then I stay still. And once again, I just define a p phi epsilon as just being this operator that I evolve to my dynamics, and I Q if it is outside, and I put here my potential, like the large deviations operator in probability. Okay, so the theorem that we managed to show was that now again of course in this scenario the folklore conjecture under these assumptions they will be satisfied, they will manage to find some quasi-stationary measure. So the result that we managed to prove was first of all that the spectral radius is greater than 0. There exists a unique probability measure, which is the quasi-stationary measure for this system. And when I take log of the spectral radius, I converge to the pressure of phi minus log of that dt. So I obtain, first of all, that these lambdas are going to the pressures. So when I take the log of it. And the second thing is that I will have right and left eigenfunctions of eigenvectors of p phi. So what is eta and mu here? And when I combine both of them, what I obtain is a phi penalized quasi-ergodic measure, not on M, but in this support of this measure. Okay, and when epsilon goes to 0, I converge to the unique equilibrium state. The fact that I have the support here is slightly annoying, but this is a fact of life rather than like we just did not manage to prove it. So and it's problematic in the case that when you are taking your equilibrium state is in a region of lambda, and this region lambda, it is something that you have some cyclicity here. So if you have some sort of cyclicity in your counter set, so you have some problem in trying to show this. However, you can do something which is quite similar to stochastic stability, and it works. However, there is a way of removing this support of new epsilon to M, to the state of interest. And then you just need to assume that the equilibrium state that you are converging to is mixing. So then everything works well, because now it's not periodic anymore, it's aperiodic, and then life works well. Okay, so just a small recap of what we have talked about in this talk, right? So we started with some map T that goes E to E, and you would have some expanding repeller lambda, and we had some open set, which is contained in the complement of the repeller, and we defined our region of interest as being E set minus this forbidden neighborhood. Then what we have done is that we induced an absorbing Markov chain using the dynamics of T, and in a way that this Markov chain is close to T and is absorbed at the forbidden region. Then, given some Holder function phi, we show that there exists a phi penalized quasi-ergodic measure on M. And then we have done stochastic stability, showing that when epsilon goes to 0, we manage to retrieve this equilibrium state. So this converges in a weak star topology and also obtain the pressure. And this allows you to, for instance, in a computer to estimate, or at least try to compute the equilibrium state of NU. So my understanding is that there are two ways of doing this. So there is an effective way that is via periodic orbits that some people work with. And what we are saying is that you could also do via this method, that you would be just taking a small perturbation of your system, then you can easily compute the transition kernels of it. And because you are using some sort of additive noise, then they are really nice, right? And you can use, for instance, Eulen's method to find the right and left eigenvectors of it. And when you combine, you obtain a measure which is close to the equilibrium state. So that's it. So thank you very much for your attention, and that's it.
Thank you very much, Matheus Manzatto. Yeah, thank you very much. Yes. So, question, comments, remarks from the audience. If you have question, just unmute your microphone. Yeah. Maybe let me begin with some maybe very general question. So I have to say first that I am not very familiar with all this ergodic theory and this probability, but I always have a request in mind, which is, do you know the so-called synchronization phenomena, for example?
Synchronization.
Yeah. So you have like the phase oscillators, and you have randomly distributed. I mean, you have initial configuration, and then when time goes to infinity, they in the phase they convert to the same phase. Maybe sometimes they can rotate. Okay. So synchronization. So my interpretation of synchronization is that they are like locally or even almost globally relative equilibrium. They are equilibrium in the rotating frame, for example. Okay. So for example, many people are interested in this because they believe that there are many applications, like to explain the synchronization phenomena of a butterfly and neural network, this and that. And now they want to add the noise into the equation. And somehow there are two expectations. Either, okay, let's suppose that the noise is very small in some sense, okay? Either they believe the noise is small. The noise is small in some sense. For example, the amplitude is very small, for example. And then there are two expectations, two scenarios. Either they believe that this synchronization phenomena is not destroyed, after the noise. They may be just like this noise, but they still converge in some sense to the synchronization state. Or they believe that even sufficient small noise can induce like an oscillation or transient state, like a periodic phenomena. And I am curious, if I have this thing in mind, how can I apply your theory to have some insight to this problem?
No, I see. So the method, this is a interesting point that you
I see
are.
my T. Yes. For example, you have in your setting, you have a T, the map, you have a repeater, you have a yeah. So maybe
I see, and then you take some T omega that is closed, and you want to see that there is some synchronization. So the thing that we were trying to work with here is that what happens before synchronization. So in the regime of synchronization, I do not know much about it, but I could understand more or less well what happens before. So that was more or less the goal in some sense.
Yes. So I think in my opinion, I'm not very sure. I think a stochastic stability means that when the noise is very small, we still see the same phenomena, right? In some sense. Yeah. And
I think.
Yeah. Sorry.
No, yeah.
I mean, yeah. Please, yes.
No, I was just saying that it depends a bit, right? Because like if T already has an attractor, then I can see that putting a bit of noise, it would make you to have the same sort of phenomenon. So you still have some sort of synchronization. So like if you have an attractor, then if it is really small, you would have what people call random attractor, right? However, it also may be the case that you have T which doesn't have synchronization.
Yes,
if I'm not mistaken, this is the case in some maps. So you have some T that goes E to E that you do not really have some sort of synchronization here. However, when you put a bit of noise, then you would have synchronization in this case. So there is a really nice paper of Froiland that I think the name is I think it's noise induced. What noise induced? Sorry, I need to find the name.
Sure. Maybe you can send me email. Yeah, thank you.
Yeah. So I'm trying to remember this. The name of the paper is from Flandoli.
Yeah. I see. So basically, you are telling me if the global, because synchronization is like a global stable equilibrium in some sense, and the small noise should not destroy that. But sometimes if there are some repeater or unstable dynamic, then now then the noise can matter.
Yes. Yeah, the name is synchronization by noise. I was just looking here.
Yeah. Okay. So
this happens in SDEs. Yes. Yeah,
please.
No, I was just saying that in SDEs, this tend to happen a bit more often than for discrete maps.
Yes, and but today I think let me make sure. So today all of your results only applies to discrete map or also to semi-flow.
No, this is a really important point is that we can do this for maps. However, we don't know yet how to do this for flows. And the reason being because the theory of hyperbolic dynamical systems for maps is really like everything works really well, but for flows is not that nice, right? Because when you're talking,
my first question.
I see. No, because for flows, what you do is that you have a central direction, right? That is the flow direction, which you don't have hyperbolicity. So you need to be a bit smarter to deal with this central direction. And then when you try to do this type of thing using SDEs with like you could take a flow, let's say, and then you would like to add the noise like this, right? So it would be something like this plus
W something. Yes, exactly. This is exactly what I have in mind. Yes.
Yeah, when epsilon going to 0, and like we do not exactly know how to prove a similar result for flows, at least yet. But it
here
would
I
be
have
really interesting.
But here I want to make sure. But for example, we have a flow, but sometimes if we, for example, we consider like a periodic solution, like stability of periodic solution, flow, okay, in smooth dynamical system. And we can consider Poincare map on a Poincare section, and then we still have a problem of maps. And we can translate the solution and the local stability in terms of the discrete dynamic on the Poincare section.
Yes.
So which means maybe on the Poincare section setting, we can still apply your result. I think.
No, this is
or we can
really
consider Taiwan map, for example, discrete Taiwan map. High-end map.
Yeah. No. For Taiwan map, I because I do not really know if there are equilibrium states for the Taiwan map, right? Because the Taiwan map of let's say an Anosov flow is not really Anosov, right? So it's a bad flow. So sorry, it is a bad map in a hyperbolic point of view. So, but I liked a lot this idea of the Poincare map. Of course, there is always the problem, right? Because if you take a flow and like if the Poincare map is mixing, then the flow may not be mixing, right? Because of this whole problem. But maybe if your original flow is good, you can get around it. So yeah, no, I liked a lot of this suggestion. So this is something that we have not tried to do.
Yeah. So I am trying to see how at least in Taiwan how people found differential SD or not SD but the differential equation can apply your result. Yes. Somehow I see for flow there's a part. But have you ever thought of generalizing your result to flow to SD? Because you mentioned there's a center, like a tangential direction of along the flow, but does that really matter? Because maybe you can portion out this direction, because it's just it's not really something external, right? It's inside the flow. I don't know how to say that.
No, I completely agree. And we have tried to do this because the problem is maybe how our like the proof of our theorem goes. I did not talk about the theorem, but the proof is essentially something like this. Okay, so okay, so just for the record, so it's something that. So you have what we call local and global problems.
Yes.
And the local is the easy one, okay? So the local is the following. So if I have my lambda, so I have some t, right? That goes e to e, and then I have like lambda that we, lambda that we define as the intersection of t minus m M. So, and then you will just want to understand the points that remain M forever. And we are assuming that T that goes lambda to lambda, this is, for instance, uniformly expanding. So what one can do is use the dynamical decomposition. That is like, if you define R as the closure of this periodic point. So I have R here and P to be the P, which is T periodic.
Yes.
Then it is a really nice set because you can decompose this R, there are a bunch of theorems of it in finitely many sets. So this means disjoint union of Rn such that this T of Rn you are topologically transitive.
Transitive, yeah.
Yeah, and like these Ri, it doesn't matter much, but these Ri's you can further decompose it into. So you are in a situation that these Ri's here. So this is Ri. You can further decompose it into R1 to Ri and I, such that you have a cyclicity here. And if you take the correct power, you are mixing each of these parts. So the local problem that we call in the paper is just taking a neighborhood of these Ri's. Okay. So you just take a neighborhood of these Ri's, and this is not really problematic to solve. What is problematic is when you take the whole lambda, and the whole lambda is a bit harder to.
The whole repeller.
Yeah, the whole repeller is a bit more challenging, and the proof goes. But this one is not problematic to solve, and the proof is simple, in the sense that you would have your operator P, right? That is expanding of f of t omega here. And what you can do is look to the pre-dual of it, that it would be just the transfer operator, the expected value of the transfer operators, okay? And now you need to pay a price that is that so here that one, and here is my neighborhood M, which is here, okay? This transfer operator that I'm defining is sum of f of y divided by t omega. I'm saying that is one dimensional just to make life easier. Then I take the derivative, and this is the case. Okay, so because I'm taking a small neighborhood, so the pre-images of this point of this M are inside, and then I'm just taking the average of these transfer operators. And the whole point is that now, let me put an epsilon here to say that is the noise. If epsilon is small, then what you have is that this perturbation is really close to the regional map. And if you are in a expanding regime that you are here, so here you have some sort of spectral, you have quasi-compactness. So this is quasi-compact. And then you're in a situation that this is compact and this is quasi-compact. And you have that the spectrum of these two things is really nice, and you can really say that they are close to each other. And because of the folklore conjecture that I'm saying, that is right and left eigenfunctions, and this thing, and to find invariant measure here is also right and left eigenfunctions, then you can show that everything is going to where it should go. However, when we look to flows, this is not that easy. So for flows, one cannot do this type of spectral picture because the generator of the flow is degenerated. right? It's extremely degenerated. And my understanding is that you only obtain this exponential decay of correlations because of an argument of people like Dolgopiat, for instance, that they show that there is a non-trivial cancellation of it. So just using the spectrum is not enough. So one needs also to use some dynamics, and we are slightly stuck on how to show this. But this idea of that you proposed about the Pancreas map gives me some hope that it may be able to connect these things.
Yeah. I can give you like a also folklore, you know, setting to make a smooth dynamical system into a discrete one, and they are closely related. The one is you consider dynamic on the Pancreas map. Yeah, this is the one thing. The other is very natural. You consider discretization in your time or in your space. Now you have map. Okay, then your how to say mesh size is your you know when you take some limit of your limit size, you recover the original smooth dynamical system. So now you have now two small parameter. One is your noise epsilon. The other is a mesh size that we call h. Okay, then maybe when h is positive, we have a map, discrete dynamical system. And suppose I can apply your theory. And then now I have to take the other small parameter h10, so tending to 0. I think this is something also a bridge to your result and to the smooth dynamical system setting. Yeah.
No, I see.
Just a remark. Yes. And thank you, very nice. And can you go back to your slide, page 38?
It's almost here.
Yeah, my understanding is there are 5 assumptions, right? Oh, no. What are the assumptions? What is the conclusion?
So the assumption is that I have that my repeller is uniformly hyperbolic, and my chain is constructed using C2 perturbations, basically.
And then there are 5 conclusions.
Yes,
like
exactly. Yeah, there are a lot of text here. I wanted to write with less text, but I did not manage.
Yeah, thank you. But I mean, I just want to see that. Yeah. So I'm wondering if somehow you can generalize your result to flow. How can I translate everything, your conclusion layer to the SDE setting? Yeah.
Yes, so I think it would be like you would need to start with some good flow, right? Some another. Yeah, the problem is that so whatever good flow would mean, right? And then this would be the SDE, right? The perturbation using the Brownian motion. And then what you would like to do is to look, instead of this operator here, you would like to look to the generator, right? So you would have an SD and you will look to a generator, and then you would look, instead of like satisfying this equation here, you would have some PD such that this would be satisfying. So it would be the Fokker-Planck equation here, right?
True. Exactly. This is what I have in mind. Yes, true.
Yeah, and then you would have the other one that satisfies the zeta would be solving the Kolmogorov equation, and then you would be combining both of them and hopefully obtaining, so you obtain a quasi-ergodic measure as before, solving with the solution of these two PDEs, and hopefully if epsilon goes to 0, you obtain equilibrium state for the flow.
So, can I say all these 5 conclusions give me saying that when the noise is very small, nothing really changed a lot?
Like yes, exactly.
It's like a very stable, like the perturbation, noise perturbation, it's not really catastrophic.
Yes, exactly.
I see.
Yeah, but what is interesting here is that we are talking about the repeller, right? And
Yes.
not the attractor. Yes, so that
Yes.
is
Sure.
the key
Yeah.
point.
Yeah.
Because
This is really
the repeller is extremely unstable, right? And even though you are in a stable thing, things get quite stable if you're looking through the lens of conditional ergodic theory.
Cool. Very good. Sorry for very long discussion. And so, any question, comment from the audience?